There we go.
Hello
Hey,
there.
Aaron, how you doing today?
Good, Mike. How are you?
Doing great. So I take it you're going to come on and talk to us about DevSecOps and security and chaos engineering.
You got it.
Okay. Well, I'll let you take the floor and I'll bow out. And go ahead if you want to share the screen.
Okay. Oops. I'll be back up here. You see
There
it?
we go. That's it.
All right, great. Thanks. We'll get started. Thank you, everyone, for having me. I'd like to thank Patrick Dubois for and all the crew at all the talks online. This is a great event. I've never seen it. I don't think I've ever seen a greater lineup of speakers than now. And make sure to stay tuned to Quinny Pig's talk after mine, as well as Jessica DeVita. Jessica DeVita's will be more in depth than mine on a lot of these concepts, but I'll be there watching that talk. So without further ado, I'll get started on my on the concepts of applying DevSecOps to chaos engineering. In this session, I will cover a lot of things pretty quickly. I've given this talk in a shorter amount of time, but I think we'll be able to cover the material this amount of time. So areas I'm going to talk about combating complexity in software. I'm going to talk a little bit about chaos engineering. I'm going to briefly touch on resilience engineering, which is what chaos engineering is a part of in terms of software. I'm going to talk about how both things apply to cybersecurity. I'm also going to talk about what is security chaos engineering. A little bit about me. I am the CTO and co-founder of Verica. I co-founded Verica with Casey Rosenthal, the creator of chaos engineering at Netflix. Prior to that, I was the former chief security architect at United Health Group, former DoD and NASA, as well as I'm a frequent speaker on the chaos engineering space. I'm the O'Reilly author of the security chaos engineering chapter for this book I'll talk about in a little bit, as well as I will be releasing a O'Reilly book on security chaos engineering in June. So yeah, let's get started here. Oh, I also led the Chaos Slinger team at United Health Group, which I'm going to talk about in my slides. Chaos Slinger was the first ever application of Netflix's chaos engineering to cybersecurity, and we'll get into that. So what is the crux of the problem? The crux of the problem is that incident outages and breaches are costly, and they seem to be happening more often. It's kind of the crux of the issue here. It's just about any day you can pull up the news and find massive outages, especially in we're currently with this COVID situation. We've never seen technology being stretched at the limits it is being stretched at now. So outages are becoming a norm, and they were already becoming a norm before that. So why is it do they seem to be happening more often? I'm going to give a few opinionated answers to this problem, I believe. But also they're grounded in research that I've done. It all starts with combating complexity in software. The complexity, where does complexity come from in software? So Sidney Dekker is one of the foremost authorities in the world on safety engineering, especially in terms of accident investigations. He wrote a couple of great books, Stripped into Failure, Field Guide to Investigating Human Error. Those are great books to read. It'll fundamentally blow your mind. What's funny is they're not even written about software, but you can directly apply them to what we do. But he likes to say that the growth of complexity in society has gotten ahead of our understanding of how complex systems work and fail. So complex systems are a term in applied sciences, right? It doesn't mean a complicated or complex system, our system that's complex, right? They have certain characteristics, meaning out of the operations of a complex system, you have emergent behavior, unpredictable behavior. A human cannot mentally model its behavior. It's impossible to diagram or model a complex system. The way you understand it is by interacting with it. And I'll expand on these concepts a little further. So if you haven't ever seen these diagrams before here, these are called the Deathstar diagrams. But it used to be there was just Netflix, Amazon, Facebook, the FANG companies that were developing systems that looked like this, meaning that every dot you see in the Deathstar diagrams here are microservices. But the problem with this is that our systems have evolved beyond our human ability to mentally model their behavior. And what's happening now is everyone is now building systems that look like this. And with this brings a whole new kind of problem. Okay, I love showing. This is actually a piece of software from Netflix called Visceral. Originally called like Flux, I think. But I love showing it because it shows. This is a brief snippet of microservice transactions from Netflix. But what it does is it shows kind of like the inherent complexity in operating systems that are so disparate in how they communicate and complex and the complex patterns in which they interact. And it's very difficult for a human, even with this small couple microseconds snapshot here. It's very difficult for a human to understand what's going on in any given point of this, the system. And that's the nature of the problem, is that the speed, scale, and complexity of our modern systems make it very difficult to understand them, let alone continuously change and operate them. So where does this complexity come from, right? I mean, so we are now, so I'll talk a bit about the nature of complexity in software, but all these techniques you see up on the screen here are for everything from microservice architectures, cloud computing, immutable infrastructure, like your DI, distributed, immutable, and ephemeral, or your auto canaries. All these technologies are directly related to delivering value faster to customer. But what they're also directly contributing to making our systems more complex for humans to understand. But the state of security is still mostly how security mostly approaches engineering. We're still mostly monolithic in how we approach solutioning. We're poorly aligned in terms of how we address solutions in software. A lot of the approach to security is still stateful in nature. And requires and what I mean by expert systems is that they require domain knowledge. Is that you can't just pick up a Palo Alto firewall and start working with it. I mean, it's not like it's Palo Alto. It's just like it requires some kind of training or expertise or to work with it versus where a software engineer can easily pick up something from GitHub and start working with new tools and capabilities. So what is the answer to complexity? I mean, the most logical common sense response would be to simplify. Well, unfortunately, software is officially taken over the stack. And complexity is inherent in how we build software. That's the new OSI stack you see. Software only ever increases in complexity. There is an old saying in software that there's no problem in software that can't be solved through another layer of abstraction, but at some point that abstraction starts to break. And I'm going to expand on that. So software complexity, where does complexity in software come from? There's a paper written, I think it was in the 1980s, called No Silver Bullet. It explains where complexity comes from in software. There's essential complexity and accidental complexity. Essential complexity comes from things like Conway's Law that states that organizations are destined to design computer systems that reflect the way they communicate. Well, a certain company communicates a certain way because that's a reflection of how they operate and deliver value to customers. So it's hard to change the software without changing the nature of the business. So you kind of inherit that through the systems and software that you build. Accidental, there's two theories on accidental complexity, but accidental complexity comes through how we choose to build the software. And there's two camps on this. Some people believe you can reduce accidental complexity. Other folks believe you're just moving it around. But really, the answer is not reducing it. It's actually navigating it. And I'm going to explain how chaos engineering helps us with that. Dr. David Woods is one of the world's foremost authorities on resilience engineering in medicine. And I love reading all Dr. David Woods' stuff, as well as Richard Cook and other folks in the space. Is that you can actually just read it. And it kind of makes sense in terms of software. So Woods' theorem is that as the complexity of a system increases, the accuracy of any single agent, meaning our human's own model of that system, decreases. So as the system becomes more and more complex, it's more and more difficult for us to model how it works in our head. So what does all this have to do with our systems and how we build things? Well, how well do you really understand the systems that you build? I'm going to posit that question. Okay, John Allspaw likes to say that real work is messy, right? And systems engineering is really messy. We kind of forget that, and I'm going to explain kind of what I mean by that, right? So I spent a good portion of my career as an architect after I got into security, and then we love to think that like our the way we approach building things is like we have this nice plan, we got resources, but we're gonna we got 3 steps, and we're going to be there, and we got a nice 3D diagram, that looks pretty cool, right? We got code, we do kind of, I think we know what's going on, right? So we go forth, we build, and we deliver, right? But what happens is after a few months, right, is that our systems slowly evolve to a state of unknown. And what do I mean by that? What I mean by that is, so after a few months, or even sometimes after a few weeks after we go live, is that there's a outage on the payments API. We have to hard code a token, or Google hires our, I don't know if it's the Google, but like Google, let's say somebody hires your best software engineer. Somebody else new comes in, or you have an expired certificate, or marketing comes down and says we got the pricing model wrong. We got to refactor. Right? It's our system slowly, through a series of unforeseen events, our system slowly drift beyond our understanding. And this is what I mean by this, I believe, is also part of what contributes to the number of outages and incidents we're seeing, is that, with the complexity, size, and scale and speed we're now delivering at, these kind of unforeseen events are more and more difficult to navigate and understand. After years, it just kind of grows and grows and grows. Right? And the point I'm trying to make here is that our systems have become more complex than we remember them. Remember, this is very difficult for a human to mentally model any point in this operational state. So what does all this stuff have to do with security? Okay, like this is security talk, right? Well, failure happens a lot. Right, and it's a failure is the normal state of a system. I have a slide later in here that says that no system is safe or secure by default. It takes a human to create it, and it's like we have a responsibility. The level that society depends on technology, it's never been more apparent than the given situation right now. But we have responsibility as engineers to ensure that. We build highly reliable, secure, performance systems so that the world can depend on. So the normal condition is to fail. Okay, that is the normal condition. It's humans. It's our ability it's improvisation. It's our ability to respond and keep the systems going is what creates resilience. We as humans, we need failure to learn and grow. The things we build are no different. So I love this quote from Scott Sagan. I got this from John Osborne and John Osborne's slides, is that what we think would have never happened seems to happen all the time. And it's kind of the truth, is that, like, if you would have thought that an outage or something was going to lead up to an outage was going to happen, you would have fixed it before it caused the outage, right? So how do we typically discover when security measures fail? Well, unfortunately, it's typically through security incidents. Is that that's kind of how we found out. Oh, wow, it didn't work. But the problem with this is it's too late. By the time we detect it and we launch an incident, the damage might have already been done. So a lot of times, security incidents are driven through I put a lot of John Allspaw, but I learned a lot about resilience engineering through a lot of the things that he had taught me. But is that what I mean by vanishing traces is a lot of incidents are launched through like log events, alerts, but those are just footsteps in the sand, right? Like, what about all the log events? I love there's a lot of security vendors out there that will tell you that they can ingest all your log data and then they can predict what's going to happen in the future. Well, what about all the log data that's never written? I mean, so software engineers are required. It's in order to have a log event, it takes a software engineer to write it, to throw the event. But what about all the log events that were never written? I mean, as a software engineer, I never prioritized. I prioritized features and functions over log events, right? So it's important to understand about all the events that we don't have, and that's really what the observability movement is sort of about. It's about it's about really trying to better understand how our systems work internally through their external outputs. So security, the point here is that security incidents are not an effective measure of detection because at that point it's too late. I think I already mentioned this, but a lot of times in security, we see the name, blame, shame game around human error and that humans are the fault. Phishing has been a huge boon to that angle on things, but it's actually humans are the ones that create the security. So to point to humans as the problem is never going to solve anything. So it's important to recognize this. We're starting to get into chaos engineering stuff here. It's important to recognize that people operate differently when they expect things to fail. Okay, so we're normally during an incident or an outage. This is what happens. People freak out. Okay, and so maybe the security incident response team may not be freaking out because they're used to dealing with it. But if you're a software engineer, you're worried that like, oh man, I know I shouldn't have pushed that code, or you're concerned that this could be you're going to get blamed for what happened, or this could be the breach. And this here is not a very good learning environment. Like when people, because immediately within 15 to 20 minutes of an incident outage, the CEO is the call center is overloaded. The CEO is asking questions like, "Get that thing back up and running. We're losing money as a company." Anyway, that's not a very good environment for learning. But we don't do chaos engineering here. Okay, this is we do chaos engineering here, and what I mean by that is that like there is no outage, nothing's burning. There's no outage, nothing's burning, nobody's freaking out. We proactively learn about our system and its failure before it causes pain. And I'm going to expand on this. So what is chaos engineering? And a lot of people have been talking about this today in different angles, and I'm just going to cover it again. Is that chaos engineering is the discipline of experimentation on distributed systems in order to build confidence in the system's ability to withstand turbulent conditions. Another way I like to describe it is it's the idea of proactively introducing turbulent conditions into a system or service to try to determine the conditions by which it will fail before it actually does. It's a learning exercise. It's a way for us to surface failure and fix things in production. It's not about breaking things in production. It's about fixing them. So there are a number of companies. I'm tracking about 1,500 companies now doing chaos engineering. This is wide varieties of maturity. But it really began at Netflix. Elements began at other FANG companies, but Netflix is really the place where it became a thing. Principles of chaos.org is very, very important to take this down. All these slides will be shared later, but this is sort of the rule book, so the guidelines that you follow. So there are now 2 books on chaos engineering, like I mentioned before. Briefly mentioned. Netflix wrote an original chaos engineering report for O'Reilly. That was about 70 pages. Now we've just released a full book, a full animal book on chaos engineering. You can find it on Amazon, as well as I've got a slide at the end here that has a link to get a copy of a free one mailed to you. So chaos is used to establish order. It's not about making increasing chaos or just causing problems in the system. We already have enough of that. So I like to break down chaos engineering, or I guess instrumentation, into 2 domains: testing versus experimentation. So testing is the verification or validation of something you already know to be true or false, meaning you know what you're looking for before you go looking for it. In our case, in security, it would be like a CVE or an attack pattern or a signature. Whereas experimentation, we're trying to derive new information it previously did not know. That's where chaos engineering sort of fits in. We're experimenting on the system proactively to learn about its behavior. So the Chaos Monkey story, I'm going to try to share a few different things about Chaos Monkey story. So it's important to recognize here that Chaos Monkeys is a little over 12 years old now. But Chaos Monkey came out of Netflix's cloud transformation. A lot of people talk about how, chaos engineering, we can't even do the DevOps. We can't even, we can barely get in the cloud, and, that's just way too advanced for us. Well, Netflix, it was the beginning of their cloud transformation when they spawned the need for a Chaos Monkey. So it's a key way to sort of, so it's not odd to find yourself wanting to experiment with chaos engineering during a cloud transformation effort. Chaos Monkey, if you're not familiar with what it does is proactively during business hours, it will bring down, pseudo-randomly bring down an AMI in Amazon, what that did was is a lot of people think they're just causing chaos, right? Well, what it's really about is Netflix has no chief architect, no authoritative arm to force engineers to do things. At least at the time that I know Casey was there, is that it's about putting a well-defined problem in front of an engineer. Is that if my service can be exposed to this chaos monkey, or it can be exposed to these kind of problems, I'm going to design my service to be resilient to that sort of problem. It was actually the AMIs disappearing was actually a problem that Netflix was having early on with Amazon at the time. AMIs were just disappearing. So Casey likes to say that the purpose of chaos engineering is not to break things on purpose. If we are trying, we're trying to fix them on purpose. And it's also, he also likes to say that I'm pretty sure if I wouldn't have a job very long if I wouldn't want breaking things all day. So what is security chaos engineering? Okay, so I like to refer to security chaos engineering as as continuous security verification. Okay, it's about proactively managing and measuring how effective our security is. So it's about correcting our mental model of how we believe our security works versus how it works in reality. And because of some of the problems around complexity, speed, and scale, and it has caused it's been difficult for us as engineers to ensure that security is always working the way we intended it to, especially when software engineers are delivering code so fast, right? And things are auto-scaling and changing on a constant basis. It's very difficult to ensure that our security works the way we need it to, when we need it to, without some kind of constant instrumentation post-deployment. So it's about reducing uncertainty by building confidence. How the system actually functions versus how we expect it to. Expecting it is basing your engineering on hope versus solid instrumentation, and that's what this is really about. Use cases for that you can use security chaos engineering. There are more here. I was only the beginning of this. That doesn't mean I know all the ways it can be applied. And if anyone ever applies it in other ways, I'd love to hear about the stories and how you're applying it. Here's the ways that I've used it in the past and the ways I believe it can be used. Is it's very valuable in instant response. And I'm going to talk about that here in a second. It's great to validate runbooks, to ensure that you have the right log data, to ensure that to validate security controls fire when in certain conditions. It's good to validate solutions architecture, whether that be in sort of your staging environments. It's okay to do chaos engineering in staging and not in production. A lot of folks always talk about online. If you do the Googles, people talk about you do chaos engineering in production. Well, there's a lot of value still in staging. Okay, you can still learn a lot, but the goal is to take a leap of faith. Is what I like to call it, to production. But it's also great for compliance. Chaos engineering, it basically proves whether or not a chaos engineering experiment proves whether the technology that you built either works the way you think it did or not. Line that up with a compliance framework, and you have every chaos experiment has compliance value. It's also Prima Varani, when she was at Pinterest, started doing some experiments around improving log data by proactively introducing security failure conditions, to try to determine whether or not the log data that during those events generated, or the controls generated, was actually valuable. Because during an active incident, you're not looking at the value of log data. You're trying to figure out what the heck happened, stopping it, and getting the system back to a point of continuity. Instant response. So I'll cover incident response a little bit. So security incidents are somewhat subjective in nature. No matter how much money you spend, no matter how many people you have, you still don't know when it's going to happen, where it's going to happen, why they're doing it, who's doing it, and how they got in or how they're trying to get in. Right? You hope that what you put in place can tell you those things, but still you don't know until it actually happens. Right? So you're hoping that what you put in place can tell you whether these questions are true or false. But what chaos engineering does is it allows you to proactively introduce the failure conditions into the system, and you can now know the point at which an incident started and measure how effective was the team. Did we have the right skills? Did the technology work? Did the controls fire into that condition? But there is no active incident. Remember, chaos engineering, there's no active incident. Nobody's freaking out. Right? People are learning. You can learn that if things aren't working the way they think they are and fix them, so there is no pain. And the nature of the issue is that the response is the problem with its response. We can be proactive through these new techniques. Like I said, when outages happen, people freak out. It's not a good learning environment. In chaos engineering, like I said, like I'm articulating here, it's about making the post-mortem your preparation exercise instead of the after-the-fact exercise. I'll talk a little bit about Chaos Slinger. Chaos Slinger was a project that we built at United Health Group when I was there. I was a little over a year and a half ago. But it was the first ever application of Netflix's chaos engineering to cybersecurity. It's still a valuable tool and open source project on GitHub. It gives you the framework on how to write experiments in terms of Python and Lambda. So if you go out there on GitHub, you look for Chaos Slinger. There's an opt-in, opt-out model. You get more of the example code and framework, and there are quite a few people using this. A lot of people, what they do is they fork it and sort of write their own. They get the idea. This is how you write it. They start writing their own. So I'm going to give a brief example of how Chaos Slinger works to start to understand, so you can frame it up in your head on how a security chaos experiment works. Okay, so the primary example we chose with Chaos Slinger was we wanted an example that when we open sourced it, because it was the first open source for United Health, first open source tool for United Health Group. We wanted an experiment that a wide body of engineers could understand. And for some odd reason, firewall misconfigured ports kind of seem to be happening all the time. Still, you think that would be a solved problem, but it's not. And so we figured kind of everybody knows what a firewall is, and everybody kind of understands what it does, whether you're a software engineer or you're a security engineer or a network or QA. So our example was Port Slinger. So what Port Slinger does, it was proactively introduce a misconfigured or unauthorized port change in Amazon. And what we did was we started doing this on our Amazon instances, and we found our expectation was that the firewall would immediately detect and block it, and it'd be a non-issue. We found out was about 60% of the time that was true, 60% of the time, but 100% of the time the commodity cloud configuration management tool caught it every time and blocked it. So proactively, when there was no incident, no outage, we learned that some of these things weren't working the way we needed them to. It was actually, the issue was a configuration drift issue that we fixed because there was no outage, no pain, no downtime. We fixed it. Okay, let's move on, right? So after both controls fired, we expected enough data to generate an alert to the Security Operations Center, the SOC. That happened successfully, but the data went to the SOC. The SOC analyst didn't know what Amazon instance it came from. Now, as an engineer, you can say, well, you can map back the IP address. Well, mapping back the IP address could take a few minutes, not to mention if there's something called SNAT. SNAT is a thing. SNAT intentionally hides the real IP address. So it could be anywhere from 30 minutes to 3 hours. If it's $1 million a minute, that's a lot of money. But we proactively learned all we had to do was add a pointer, and at a pointer, and it was fixed. Anyway, so we were proactive. We were able to proactively learn about all these things that could have caused, not to mention cost the company money, the customers pain. Especially when we talk about people's healthcare, it's very important to them that the healthcare people get that right. So I'm going to leave you with two things. I feel like I've threw a lot of John Osborne in this presentation, but I got a lot from him. But it's about we need to stop looking for better answers and start asking better questions. So right here is a link to the new book that just came out. Literally, we just got our copies of the book today in the mail. The authors did. Actually, the core authors didn't get it, but the contributing authors did for some reason. But anyway, here's a link to the book, and I'll open up for questions.
Thank you, Aaron. Okay, so let's see. We got a couple of questions here. We're kind of running out of time too, so I'll try to be quick on them. Okay, let's see here. So the first question is, talks about confidence is only as good as a previous practice. Isn't it like mental trap?
Oh, can you say that again?
Confidence is only as good as a... Let me check here. It seemed to be scrolling up. Confidence is only as good as a previous practice. Isn't it like a mental trap?
Well, I guess I think I know where that's coming from, but we can expand on this in the Slack.
Okay.
But the confidence, the confidence is you're getting instead of saying I believe when X occurs in my system, my assumption is that when X occurs, Y is the response, right? How often do you actually ever instrument that? So what we do is we actually instrument that. It's a post-deployment thing, not a CI, not a CD thing. It's post-deployment where these sort of already sort of problems start to occur. And we're building confidence that the system is still functioning as it was designed or coded or intended to. And that's where the confidence comes from. But I think if I understand where you're coming from, it's really kind of only as good as the experiments, right? And the number of experiments you run, how often you run them. And that's very true. But what it also, I think this might be another piece you brought up is that it helps us understand how effective some of our other measures might have been or not, the controls or testing methodologies. It's another way of providing a feedback loop to those mechanisms and improving them. So I hope I answered that question, but we can expand on that in Slack.
Okay, then the other one says here, what could COVID-19 handling learn from chaos engineering? That's a good one.
That is a good one. I will tell you that chaos engineering and the practice of resilience engineering is a larger domain. Has never been more at a higher point of concern than right now, just because technologies are being stretched like they've never been stretched before. Yeah. And chaos engineering really is whether it's security or it's availability, but availability, I mean, like this is really a stability of our systems it's one way to proactively identify if a failure is going to happen before it does. Because the issue is that you don't know where the edge is in your system until you fall off of it. With chaos engineering, you can identify where the edge is and the points that lead up to it, and know, hey, if that only gives you 15 minutes, like to know that, like at least you have 15 minutes to notify the call center, put a statement on the website that hey, or notify key customers that hey, we're about to experience a major outage. It shows you're in control of the situation, not you're just responding to a fire drill.
This other question is probably similar to what you just responded. Is there any relations between chaos engineering, between chaos theory and immune systems?
So complex systems is where chaos theory comes from, and traditionally they've been mostly studied in the fields of medicine and nuclear power, the military. And really, it was John Allspaw and David Woods and Klein and Richard Cook that brought the craft into what we do in technology because of the role technology is now playing in society. But it's actually, if you do any of the research, do the reading, and you think about what you do when you're reading it, it's remarkable how similar and how much it relates to what we do.
Gotcha. And then the last question is, have you seen any companies actually doing chaos engineering for security?
I have. There'll be several of those companies are sort of documenting their case studies and use cases in the O'Reilly book that's coming out in June. But a lot of people are focusing around cloud and sort of a lot of it's not pen testing, it's not red teaming, it's not purple teaming, it's failure injection. Okay, so it's a little different, but it's still the same concept. You're trying to validate that all that money you spent on security is still working day 1, day 10, day 100, day 1,000, the way it was supposed to be working. And that's a lot of people focus on either container solutions or they'll focus on sort of cloud misconfiguration. But it's about accidents and mistakes that happen as a result of the complexity.
Gotcha. Sounds good. Well, thank you very much, Aaron, for joining us today. And we'll see you over there on the Slack channel.
Thanks for having me.
Hey, thank you. Take care.